Okay, I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. We thank you for your mercy for us each and every day, that you loved us even when we didn't love you. Thank you for your love for us, Lord. I just pray with us today. Help us to glorify you, Lord, what we do here this day. In your name I pray. Amen. You guys got questions? I will say this. One last example. If I have f of x comma y equal to, I don't know, ax plus by, and I want to do something like maximize that on some region, I don't know, then if I look at the gradient of f, what do I get? Right? So for this example, if I was going to maximize, so any maximum min for f must happen on the boundary of D, right? Or the function is just constant, right? Why is that? Because I'm saying if A and B are both non-zero, there are no critical points, right? There's no interior place where you could have a min or max. So pretty much that leaves you with either the function's constant over the whole domain, or you're going to find maximums and minimums on the boundary. So here's kind of an easy version of the problem we did last time. Something like this. And by the way, if you study, well, maybe you saw this in college algebra, something like this, right? Your objective function was something of this form. And maybe you might have had a place to look at your domain of consideration with something like a triangle, right? Maybe you've seen this technique called, what is it called? Geometric programming, is it? Or linear programming? I think linear programming. Basically, the moral of the story is you just have to check if you check the vertices of your region, if your variables are bounded by some sort of polygonal region, if you just check the vertices of the polygon, the maximums or minimums have to be there. Well, even from what limited analysis I've done here, you can see it has to be on the edge, right? But then something else must tell you it has to be on the corners, actually, when you think about it more. I'm not going to think about it more right now. I'm just saying. So anyway, now you guys had questions about the homework, so. Okay. Mm-hmm. Oh, okay.
Okay, that symbol at the end, that's not the partial derivative.
No, yeah, so this symbol is the symbol for the boundary of a shape. So this is the boundary. Boundary of D. What happened?
We were just flabbergasted at the fact that it looks exactly like partial D.
Oh, it is the same symbol as partial D. What? It's ultimately to give you... Well, it's because mathematicians want to write this eventually. So that the derivative of the form kind of becomes a derivative of the shape. There's this interchange between integrals over the shape and integrals over the boundary, and the form and its derivative. But anyway, that's why the notation is to make this theorem complete in its awesomeness. But anyway, we'll talk more about that later. Okay, questions? Yes, sir. We can, but then I have to steal a textbook from somebody, or go down and get one.
I have one.
Thank you. I'm sorry, I should have brought one today. I'm not thinking terribly clearly. This is evidenced by the fact that I spent like 4 hours yesterday trying to do a particular problem in a quiz I gave. And it has burnt my brain. All right, so I'm still recovering.
Page 840.
Oh, thank you. That's easy. Page numbers are awesome, aren't they? Let's see here. Number what?
3.
Number 3?
Finding absolute extremes.
Okay. Now you said 3, not 30, right?
Yeah.
Okay. X squared plus xy plus y squared minus 6x minus 1 for, we've got 0 less than or equal to x less than or equal to 5, and minus 3 less than or equal to y less than or equal to 0. And we're supposed to find the, you mind if I leave this up here for now? Okay, the min and max. Let's not forget it though. I think last time I did this, I ended up taking the book home with me. So try to remember to get it back to you. So what do we do, guys? I think it's a good idea to draw a picture of the region that's bounding things to get a kind of a grasp of things before anything else happens. So this is a rectangle, right? So x is going from 0 to 5, and y is going from 0 to minus 3. So it's something like this, right? So we're trying to, right? And so I guess the first thing I need to do is see if there aren't any local extrema. So I look at the gradient of f. That would give me 2x plus y minus 6, comma, x plus 2y, right? Yep.
How do you know if the rectangle just based off the points that they have over there? The 0 between x and 5 and x is minus 0.
Well, yeah, this is the intersection of these two. So, I mean, the inequality 0 less than x less than 5 is a vertical band between the lines x equals 0 and x equals 5. And then the other one is a horizontal band. It's between y equals 0 and y equals minus 3. So you take the intersection of those two bands, that's where both inequalities are met. That's this region.
He's not drawing the function, he's drawing the function area where the function is. Yeah.
Oh yeah, I wouldn't try to draw the graph. No. This is just the domain of consideration. Are we good?
Yeah.
Okay, so you probably know what to do here past then, right? No? So we set this equal to 0, 0, look for solutions. That's not too bad because these are lines. So I get y is equal to 6 minus 2x, and y is equal to minus x over 2. So this gives you 6 minus 2x is equal to minus x over 2, which gives you 12 minus 4x is equal to minus x, which gives us 12 is equal to 3x, so therefore x is equal to 4. Y is equal to minus 2. Looks to me like we just have one critical point. Does that point even matter? Is it inside the box? What's in the box? Sorry. Yeah, that's right. We watched that clip. That makes sense in here. I've referred to our common experience. It's valid. 4 and minus 2, it's right in here, right? Enough of you. Oh well. You win some, you lose some. Let's see here. So f of 4 minus 2 is what? We need that for future reference. Yeah. 16 minus 8 plus 4 minus 24 minus 1. So this, and this cancel, and it leaves you minus 9. That's not the answer necessarily, but that's a possible answer, right? Then what do you do? Which is worse, a triangle or a square for one of these problems? Well, the triangle has less sides, right? But the square has nicer parameterization. So I think it's kind of, they're both awful. But let me number them. Yes? Oh. I want it to be there, though. Aw, man. But I still want there to be a +4 there. I think my brain skipped. Ah, phooey. Fine. So I guess that makes this a... -13? -8. -8 plus 4 is -4, -4, -20. What? No. 8 plus 12. 12 minus -12. Yes, -13. All right. So, getting back to the story here, we've got 4 things to think about. 1, 2, 3, and 4. I would encourage you in these kinds of problems to do some labeling. Otherwise, it's about impossible for me to see what you're doing. So, case 1, we're looking at what? F of what? There we have what? We have, what can you say about 1?
Y equals 0.
Thank you. And x is equal to x, right? So we're looking at f of x0, which is what? X squared minus 6x minus 1. Yeah, this is better than that stupid triangle problem, isn't it? And on what? 0 less than or equal to x less than or equal to 5. And then we have to figure out, is it big or is it big? Where's it small? I don't know. I guess we'll do calculus. F prime, so let me call this thing G. I'll call it G1. So dg1 dx is what? 2x minus 6. So if that's equal to 0, that tells me x is equal to what? 3? Now think about it. This is a what? This is a parabola which opens up. So we just found where the vertex is. So G, so f of what? F of 3, 0 is equal to what? 9 minus 18 minus 1, which is what? Minus 10? Yep.
Because this is a parabola that opens upward, do we know that's the local minimum?
Yeah. On the edge, anyway. But I would point out, for the sake of not duplicating work, it's probably a good move to figure out the value of the function on the 4 corners of this problem, so we don't have to check endpoints in each case. Do you see why that would be logically okay as opposed to breaking? I mean, so otherwise we have sort of some sort of like duplication of work. What's the value of the function here? F of 5, 0 is what? Yeah, 25 minus 30. Minus 1, so minus 6. All right. And what's the value here?
0.
And what's the value here? F of 5 minus 3 is equal to what? So we probably should start we should start keeping tabs on here, right? What do we got? We got 0, 0. We got 0. We got 5, 0. We got 5 minus 3. We've got 0 minus 3. We've also figured out 4 minus 2. And let's see here. We also figured out 3, 0. These are all contenders, right? Minus 1, 5, 0, minus 6, 5 minus 3, negative 27, thank you. 0 minus 3. Okay, so I'm just going to start keeping track of them over here where we can see them all nice together. All right, case 2 then. We have what? We have g2 of x, which would be f of what? 2 has what? X is equal to 5 and y is equal to y. So we get 5 comma y, which is what? Sorry, g2 of y, right? And what's that equal to? (25) plus 5y plus y squared minus 30 minus 1. So in other words, g2 of y is equal to 5y plus y squared minus 6, okay? And so what's g2y of y prime? It's 5 plus 2y. So if we set that equal to 0, that gives us the critical point on that leg, which is what? Y is equal to minus 5 over 2. I mean, it may or may not be in there. Oh, this problem is vicious. They're all in there. Okay, so that's somewhere. That's in the allowed. It's in here somewhere, right? It's in 2. So there's another one to check. 5 minus 5/2. I await the value from the audience.
I think the value for 5 would be 3 and 12.
5 negative 12? Okay. So once you guys figure out what the value is on leg 2 at the critical point in the middle of the leg, let me know. Yeah?
Looks like that would be negative 12 and 4.
I'll take it. I mean, I don't know. We have agreement? All right. How about this? Next. X squared minus 3x plus 9 minus 6. I shouldn't have taken homework questions today. I was here minus 1. Why did I do it? Man, that's the trouble. If you assign homework, people are going to ask you about it. Let's see here. See your x squared minus 9x plus 8. So again, g3 prime of x is 2x minus 9. That equal to 0 tells me that x is equal to 9/2. Annoyingly, again, in the domain of consideration. Go. 9/2. In other words, 4.5. What was that? Minus 3. I'll let you guys work on that. I'll go on to the next leg. I do want to actually answer other homework questions today. What's the fourth leg? X equals to 0, right? So we're looking at G4. I mean, this is a good question to have asked. Thank you for asking it. Let's see, so f of 0, y. Hey, that's nicer. Y squared minus 1? So, finally some variety. Haha, already covered. So sometimes you'll find a point which is, your critical point might end up at the edge, right? So you already took care of that in the other thing. Anyway, the point is, you need to take care of endpoints and critical points on the boundary wherever they occur. Make sure you don't miss anything. It's okay if you double count something, right? But it's better if you can be lazier. So what did we get for this?
If I punched in right, 41.75.
41.75. Agree, disagree? No one agrees or disagrees? That's not what you're getting? What'd you get?
I got
Okay, so let's see here. While we're double checking each other, if you look at this list, what's the maximum? What's the minimum? One of these things is not like the other. I guess it comes down to which one is this, right?
Yeah.
But I do like the symmetry of that. But the expression's not quite symmetric either, so I don't know. No, sorry, Mike. You have been, as you know, what is correct mathematically is a question of consensus. So, you know, I mean, all truth should be, should be decided by consensus and political expediency. That's generally the truth, right? So that's the smart money. That's a year. So this is the max, right? Where's min? Aha, right there.
That's nice. They showed up right next to each other on your chart.
I'm afraid. I'm a little bit afraid to look at the back now. This was number 3, wasn't it? Four comma minus 2 gives an absolute minimum of minus 13. 0 comma minus 3 gives an absolute max of 8. We win! All right. I'll accept it. All right, next. I reserve the right to not work out the entirety of this problem. Number 64. Oh yes, that's a totally legitimate question. Yes. So one of the things I have left out of the current lecture exposition is just that one. Okay. I guess I could start here. So one of the last remaining pearls of wisdom I was going to share with you is my bag of tricks about recentering functions And so if I want to find, for example, a Taylor series centered around some point, well, this one I probably can just do. I'm not sure what's the best way to do this one here. This may actually be, bless you. This might actually be an example where direct application of the Taylor series is best. Let me try out something similar. So let's just try to find the multivariate multivariate Taylor series centered at 0, 0 for, say, cosine of the exponential of x squared plus y squared. All right. So my first inclination, right, is to just try substitution. Just try substitution and see if it's helpful. And let me just take a second here to show you why substitution maybe is not helpful. So this is cosine of what? It's cosine of 1 plus x squared plus y squared plus 1/2 of x squared plus y squared squared plus dot 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 dot, right? Now the problem tells you that you only need to calculate the second order, right? It does. So that's part of the problem statement. Expand to second order. Now, sometimes the approach I'm taking right now is good. It works great, but I think it's going to fail here. And so, first of all, I don't need this, right? I can ignore that piece. Why? Yeah, it's fourth order. It's beyond what we care about for the problem. So I can say, okay, well, and what's cosine? It's 1 minus what? 1 minus u squared plus 1/2 u squared, rather. 1 over 4 factorial u to the 4th plus dot 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 dot. Huh. You know, I may have to retract my statement. Maybe this actually is okay. So this is what, and I'm saying here, a substitution, what's my substitution? U is equal to 1 plus x squared plus y squared plus dot dot dot, you know? So you'd have 1 minus 1/2 of 1 plus x squared plus y squared plus dot 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 squared, right? Plus 1 over 4 factorial. What's that? Where did the what? Oh, okay. 1 over 4 factorial of 1 plus x squared plus y squared plus dot 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 to the 4th power, and so forth and so on. So in order for this to be legit, in terms of not making a bunch of extra work for us, the question is, can we actually easily neglect everything that's in the plus dot 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 dot? And I say to you, no, we cannot do that. Because when I square this, what happens? Right. And so in particular, I've got 1 as part of that, right? And then I've got plus other stuff. I don't really care about the other stuff. Just say that for a second. And here, what happens when I raise it to the 4th power? I've got a 1, and then plus stuff. Does the 1 that's in every one of these terms matter? It does. It's 0th order. It has to be part of the answer. So in order to actually calculate up to second order correctly with what we're currently doing, I can't neglect the plus dot dot dot. I have to face it. So this isn't not a good approach for that reason. So what else could we do? Yeah?
Could you take the same approach, only at the beginning substitute x squared plus y squared for r squared?
Yeah, but I think I'd still have the same problem because then I have 1 plus r squared. 1 plus r squared squared. My answer is rather unexciting. It's just to use the Taylor expansion directly for this one. So f of 0, 0 is what? So these are the derivatives I need to calculate. If I know those, I can put together the Taylor's expansion, right? It's not super fun, but you can do it. Well, 0, 0 is what? That's cosine of
1.
yes. Which, by the way, is what we're picking up with these terms. 1 minus 1/2 plus 1 over 4 factorial, and so forth and so on. That's the cosine of 1. Now what's fxx? It's minus sine, well, let's get to the point. It's 2x, right? Minus 2x times the sine of the exponential of x squared plus y squared times the exponential of x squared plus y squared. All of that put x equal to 0, right? Y equals to 0, so it's 0, right? The evaluation bar is a nice notation here. It saves you a lot of writing. How about y? Likewise. Ow. Oh. Well, anyway, you can calculate that, right? I mean, it's a triple product. You had to use a triple product rule. You guys know triple product rule? F G H prime is F prime G H plus F G prime H plus F G H prime. That's relevant here because I have a function of x, right? A function of x, and then another function of x. I don't want to finish this problem. I will tell you what would happen, though. So f of xy, what we found is it's f of 0, 0, right? Plus f sub x, 0, 0. Times x plus f sub y, 0, 0 times y, right? Plus 1/2 fxx at 0, 0 times x squared plus fxy at 0, 0 times xy plus 1/2 fyy of 0, 0 times y squared plus dot, dot, dot. I have done this much. I have figured out that for my example, which is kind of like your example, we have cosine of 1 is a 0th order term, right? And then we figured out that this is 0 and that that is 0. So to get beyond that, I actually have to calculate the second derivatives. I mean, I can do one. I just don't want to do all three. How about that? Would one make you happy?
Yes.
What's that? You guess?
Yes.
Yes. Oh, okay. So grumpy. Delightfully grumpy. Let's see here. fxx minus 2 sine of e to the u times e to the u minus 2x cosine of e to the u times e to the u times 2x e to the u minus 2x sine of e to the u times e to the u times du dx, which is 2x. What's my u? What's your r? Squared. Of course, you know this and that are 0, right? And you have e to the 0, which is 1. So I can see from this that fxx is what? Minus 2 sine of what? Sine 1, yeah. So I get minus sine of 1 times x squared. And you know what? By symmetry, oh, I can't get the xy by symmetry. Fine. Look what you guys have driven me to. fxy. What would that be? You can differentiate either one of these. What do you want to do? I think I'll differentiate the first one. So I've got that I only need the double, not the triple product, but just the single product rule, right? That's a good reason for calculating fxy with fx, because this you only need the double product rule, whereas with this you need the triple. There's a good reason to calculate fx, the y derivative of that. So I get minus 2x, parentheses, parentheses stuff, right? So it goes to 0. Who cares? Don't calculate. You can factor out the 2x. When you differentiate with respect to y, it's outside. Why differentiate? You know at the end it's 0. Yeah. Yeah, we can. I'm this far in. I got to finish it. So this is 0. By symmetry, this is also minus 2 sine of 1. And so here's the answer. The second order, that's it.
Wouldn't it be,
These are actually not the, this is actually not what I wanted to show you when at the start of this. Number 70, you said? Yeah, hold that thought. Hold that thought. Any questions about this?
So for the homework, it said something like, for number like 54 and 55, it said something weird about like graph, blah, 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 blah. Do you want us to like show the graph, or do you want us to just graph it and like, I don't know?
I want you to do like graph it with like MATLAB or Mathematica or something, and attach a graph.
But you want us to attach a graph. It's not like just go graph it and look at it and don't do your work. It's like attach a graph.
Or if you think you can actually plot it by hand, I mean, I think I would use Mathematica or something. I mean, that doesn't look like.
I was just wondering if you actually wanted us to attach a graph. So the answer is yes. Okay.
I think so. I mean, I want you to learn. I don't know. If I don't say to attach the graph, I have this sneaking suspicion that most people won't do it. Am I wrong? I can tell from the smile on your face I am correct. I was correct. All right. I will come back to your question number 70. There is something, there's easier problems here than this that are still something I haven't talked about yet. For example, suppose you wanted to find, suppose you had f of xy was equal to, like, say, sine of x e to the y, and I wanted to find the expansion around, say, 1, 2. How would you do that? Well, there's a simple trick. What you can do is you can replace, what this means, right, is I want things like x minus 1, and I want things like y minus 2, right? How do you make x minus 1 appear from x? Well, what you do is you add 0. But you add 0 in the right way. So you do x minus 1 plus 1, e to the y minus 2 plus 2. Why do that? Pretty simple. Then I have the sine of x minus 1 cosine of 1 plus the cosine of x minus 1 sine of 1. And then this guy becomes e to the 2 times e to the y minus 2. And then if I wanted to say find the expansion of this thing around 1, 2 to second order or to fourth order, whatever, it wouldn't be that hard. What do I get? I get, well, there's an e to the 2 out front, right? I'm going to bring the, so this is what? This is like x minus 1 cosine of 1. Tell you what, I'll just do it to quadratic order. So x minus 1 cosine of 1 plus what? 1 minus 1/2 x minus 1 squared times the sine of 1 plus other stuff times what? Times 1 minus y minus 2 plus 1/2 y minus 2 squared. And you just multiply and collect the terms up the quadratic order. No differentiation, just algebra and trigonometry. What do I have? I got e to the 2. So I get sine of 1 is my lowest order term in here. So I get sine of 1. And then I get my linear term, I get plus, it looks like cosine of 1 times x minus 1. Are there any other linear terms in this product? How about 1 sine 1 times that? So I get plus sine of 1 times y minus 2. Now quadratic, where's quadratic coming from? I've got this minus 1/2 x minus, well, 1/2 sine of 1 times x minus 1 squared. Are there any mixed terms? Yeah, here they are. Minus cosine of 1 x minus 1 times x minus 2. Have I missed anything? How about the y squared terms? Looks like it's just from this one times this, which gives me plus 1/2 sine of 1 times y minus 2 quantity squared plus dot 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 dot. No differentiation, just algebra and trigonometry. Oh, and power series. Sorry. A little differentiation there, I suppose, but shall I show you a simpler version of this example? So take this, expand at 1, 2, 3. So how do you make an x become a x minus 1? Yeah, very good. Plus what? Y minus 2 plus 2. And then e to the z minus 3 plus 3. And so what do I get? I have an e to the third power I can pull out front. And then I'm going to have an x minus 1. Oh, let me rewrite this again. I have a 3 plus x minus 1 plus y minus 2 times what? Times 1 plus z minus 3 plus 1/2 z minus 3 squared plus da da da. And then you can just multiply out and see what you get. So the lowest order, I have 3. Factoring out the e cubed. Then what? X minus 1, y minus 2, z minus 3, Plus what? Plus. Yeah, thank you. Well, anyway, you guys get the idea. So I'll stop there, but. Again, that didn't work so well for us in the first example because, it's just the substitution's awkward here. All right, now you wanted to know about number 70? Okay, so. I think on first glance that looks like Lagrange multipliers to me. So you've got you have f of supposed to find the extreme values of this, right? I mean, who knows if there are any? What does this curve even look like? Do you have a good sense of it? So y squared is equal to 4 over x squared for x not equal to 0, right? Of course, x can't be 0. That's not in the solution set. 0 doesn't equal 4, so that's safe enough to neglect. And so this gives me y is equal to plus or minus 2 over the square root of x squared. In other words, plus or minus 2 over the absolute value of x. So if you trace out all the possibilities, what we're looking at here is then basically this. So it's not compact, right? It may be that it may be that we don't find the minimum or maximum or something. Maybe we find just a maximum but not a minimum, or vice versa. I don't know. So we got. I guess you have to set up the gradient of f, right? Is equal to lambda times the gradient of g. So I guess you did that probably. And so what's the rub? The algebra is weird.
I guess it was 72 that was where it was completely stopping.
72. So anyway, you guys see where to go from here. You just, y plus 1 comma x plus 1 is lambda times what? 2xy squared comma 2y x squared. And try to solve those. Those look hopeful. Number 72, though, was the troubling one? Okay, so now you may be able to solve the algebra, but I would be wary of the interpretation. Because you can think about, you see you can already kind of see you're probably going to get these. I don't know, it depends on what the objective function looks like. It may not be symmetrical. Number 72 is one of these half-disk problems, right? So it's partial disk. Oh, it's a little bit more than a half disk? Or not quite a half disk. Y greater than minus x squared plus y squared less than or equal to 4. And y greater than or equal to minus 1. And our objective is x squared plus y squared minus 2y plus 1 on this partial disk D as given. So I think it looks something like this, because like between 0 and 2 would give you just the, the half disk, right? So that's the I guess I would probably do Lagrange multipliers on the disk, and then I would probably parameterize that line segment at the bottom. Of course, if Lagrange multipliers throws at me a solution which is beyond the part of the circle that I'm actually looking at, I'd ignore it. Then that might mean that there is no maximum on the. Oh, there should be something though, because the circle is compact. You should get some solution from Lagrange multiplier. If we solve the gradient of f equal to lambda times the gradient of g, where here g being x squared plus y squared equals to 4, that will give me what? That gives me 2x comma 2y minus 2 is equal to lambda times 2x 2y, right? So I get 2x is equal to 2 lambda x, and I get 2y minus 2 is equal to 2 lambda y. Let's see here. So I can get rid of the 2's, and this gives me what? This gives me x times 1 minus lambda equals to 0, and this gives me, well, what's this give me? Y minus 1 is equal to lambda y, I suppose. Do we agree? It's been a long day. Don't trust my work. Oh, okay. Well, I first of all find the second equation somewhat useless. The first equation I like. First equation has a dichotomy. Either x is equal to 0 or lambda is equal to 1, right?
The problem is because you put either of those back into the other one makes no sense at all. Shouldn't they agree across both equations?
Both of these at once?
I mean, for the other one.
Well, no, I'm not done yet. So x equals to 0 tells me what about y? 0 squared plus y squared is supposed to be equal to 4, right? So therefore, y is equal to plus or minus 2. Therefore, y is equal to 2 is the one we're interested in. Now, if y is equal to 2, then you have to go back to the, let me underline it in red. Does that still work? So I've got 2 minus 1 is equal to lambda times 2. Can we solve that? Sure, lambda's a half. Not that we care, but so it seems to me one of the solutions to the Lagrange multiplier equations is up here. The other one is down here, but of course that doesn't count. Right? It's outside no man's land for this problem. It is in the forbidden zone. Does that make sense? I tell you what confuses me usually with these problems is when I inadvertently go from one case and without realizing it, try to put it in my other case. It's so easy to do that. That's why I really like the thing I circled in green, because there's a clear division of labor. Either x is equal to 0 or lambda is equal to 1. One or the other of those things has to happen in order for this to be 0. This, I don't know. Maybe you could. Okay, so the other case, lambda equals to 1, gives you what? Y minus 1 is equal to y. And then I'm on the same page with you. There are no solutions, because this tells me that 0 is equal to minus 1, or minus 1 is equal to 0 to maintain the logical ordering. Minus 1 equals 0. And that equation's hard to solve. So Lagrange multiplier is under no obligation to give you solutions in every case. It must be that one of those is the min and the other one's the max. Right? But whichever one of these is the min or the max that we lost, we must gain it again down here somewhere, logically speaking, because this shape is compact. So the min and the max must be attained by the continuous function somewhere on here. So if we lose a min, we pick up a min somewhere on there. Has to happen by topology. Yes, sir.
So if your constraint curve intersects your objective, you will always, and the compact conditions are met, you'll always find answers this method.
Yeah, if the constraint curve is closed and bounded, if it makes a nice loop, but it's not fuzzy, it's not missing points, if you can sufficiently, if you could make yourself sufficiently large, if you could put your arms around it, you know. I don't know. I think I can see through this problem geometrically, by the way. You know what this is? This is x squared plus y minus 1 squared. Right? So if you want the level curves of f, what are they? Oh, the minimum is going to be at 0, 1. When you calculate the gradient being 0, you will get 0, 1, right? And the maximum is going to be this right here. Right about here, I think. Wait a minute, no. No, it should be right there. Or there. Yeah. No, it's going to be this point and this point. They'll be the same, I think, by the symmetry of the problem. So the maximum, I think, is going to be, I don't know, it depends on where these points are, but it's that distance squared, whatever that is. So that's my prediction is when you work it out, you'll get the minimum is 0, and it's at 0, 1, and then the maximum will be attained on 2 points where the circle joins the line segment. My expectation, yep. That was just scratching. Ignore it.
For 71, what are we exactly solving for? Like, that's going to be in terms of some sort of complicated A, B, and C thing, or the way around, or?
Let's see here. Find the minimum and maximum distances from the ellipsoid. X squared plus 2y squared plus 3z squared equals to 1. And the point ABC. Okay, yeah, so let me set it up for you. You can do that. Now, what was your question again? Oh, the answer should be in terms of ABC. So, well, I think 1, 2, and 3 probably come into play. So, you know, this ellipsoid is something like, what did I say, x squared plus 2y squared plus 3z squared equals to 1, some ellipsoid, right? And then you got some point, A, B, C, right? And what you want to do is find the minimum and maximum distance, right? So if you think